The purpose of this lab is to investigate how accurately a computational model based on Newton's second law can predict the position of an object moving at a constant velocity. Newton's second law is a fundamental principle in this lab, which states that an object will speed up, slow down, or change direction when a force is applied to it, and how much it changes depends on its mass. Using this formula for constant velocity, there is no acceleration, so the net force is equal to 0. Regarding the process, a video of the Lego car moving at constant velocity was analyzed using tracker to identify the object's position and corresponding times. The computational model was constructed and made predictions on the object's velocity, and it was evaluated for its accuracy compared to the experimental observations. Position update formulas are used to simulate motion over time between each time step. The main results of the lab show a slight difference between the computational model and the experimental data towards the end of the recorded time. As shown in this video, the car goes in the positive x direction. The system is the Lego car, and the surroundings include the ground, the air around the car, the gravitational force of the earth, my hand pushing against the car, and everything else around the system. These are the relevant initial conditions for the observed data, which we will use later to construct the computational model. For the coding, the first image here is a visualization setup creating a ball representing the car, a green line showing the displacement, and a yellow ball showing the initial position. The initial conditions mentioned before are included here. This loop runs a simulation from 0 to 0.469 seconds. Beginning from the initial conditions and knowing the system mass, we can look a short time into the future and predict the new velocity and the new position using the update formulas. But to make these work, we need to specify the total interactions, which in this case, we make the assumption that they are 0. As a result, we notice that the change in velocity terms on the right hand of bell is always 0 because the net force is 0. So the object's mass plays no role in the prediction of the new velocity. Here in the coding output, we can see the displacement of the car to the right, and the constant velocity is shown in these two graphs. This position versus time graph of the car shows a comparison between observations and predictions, where the observed positions at different times are shown in red squares and the predicted positions are shown by a blue line. Some similarities between both datasets are that they show a general increase in position over time, which aligns with Newton's first law and Newton's second law. Nonetheless, the experimental data slightly deviates from the model, since in the observations, the car slows down slightly over time, while the model assumes constant speed. The model does not account for the small negative acceleration of the real object, hence the gap here. If we look a little closer into the possible sources of error, the car moves slightly away from the camera and doesn't remain in a completely horizontal frame. The gaps between the floor tiles, the friction from the interaction of the car's wheels on the surface, the drag force of the object as it moves through the air, and possible video tracking inaccuracies due to blur or misalignment of the camera could all cause the position data to be inconsistent and could explain why the model overpredicts a little towards the later time. If we were to flip the axis, an object that was originally moving in the positive x direction would appear moving in the negative x direction. The sign of the velocity would also change because it is the rate of change of position. The position versus time and velocity versus time graphs would be reflected across the x-axis. However, the object would still move at a constant speed in a straight line, which is seen in a position versus time graph here. For the second statement here, yes, the multiple forces acting on the car that balanced out include the downward gravitational force and the upward force from the car canceling each other out vertically. The minimal horizontal forces of friction and air resistance can be also balanced out by the car's initial push. These forces add up to a net force of zero, allowing the car to move at a constant velocity. In conclusion, the computational model based on Newton's second law is accurate to a certain extent, but when we reach later times, then the model becomes increasingly distant from reality due to unaccounted variables.